Hello, everyone. I'm going to be talking today about static application security testing tools for secure PLC programming. So if you work in the software development space, particularly if you talk to DevOps guys, you've probably heard this statement before that goes something like this. Software bugs cost 100 times more to fix in production than they do in development. Now, I have to caveat this statement by saying it's maybe not the most well-backed by evidence. It's kind of often references a paper that's from quite a long time ago that hasn't been replicated. But even if it's not like quantitatively correct, I think we can all agree that it's directionally correct. And especially in ICS, it's believable that it could cost that much more. Because anytime you have to have PLC downtime, that could cost you millions in revenue. So as cybersecurity professionals, we should be looking to avail ourselves of whatever tools we can to help us find bugs, and particularly to find insecure PLC coding as early as possible in the development process, as far left as we can find them in this graph, as far away from maintenance as possible. And one set of tools that I think is useful for that is static analysis tools. Static analysis simply is just examining code without executing it. So unlike unit tests, you're not actually running the code, and unlike code reviews, it's an automated process. So you could make an argument that under a broad definition of static analysis, manual human code reviews count as static analysis, but for the purposes of this talk, I'm talking about automated detections. And the way you would typically do static analysis is that you create this data structure called an abstract syntax tree, and then you fill the abstract syntax tree with your code. And then you can traverse that abstract syntax tree with some not too complicated pattern matching rules to determine properties about that code. Now, it's kind of a bummer that we're only on like the third slide and I'm talking about limitations already. Normally you would save that for near the end, but I think for static analysis to have an honest and comprehensive view, you really do have to understand the limitations because they are significant. So a classic example of this is the halting problem. You may have heard of this before if you come from like a computer science-y background. The halting problem is given an arbitrary program to determine whether it halts or whether it gets stuck in an infinite loop. And I don't know about y'all, but when I was first introduced to this problem, I thought, well, this is probably like kind of trivial or easy. We'll solve this first, and then they'll show us how to move on to more complex problems. But unfortunately, it's not easy. And not only is it not easy, it's not just hard, it's impossible. It's mathematically provably impossible to determine whether an arbitrary program gets stuck in an infinite loop or not. And we've known this for a long time. This was proven by the father of computer science himself, Alan Turing. And it actually gets even worse than that because not long after Turing made that proof, we got Rice's theorem proven, which generalizes it a little bit more. And this is not the most rigorous mathematical statement of Rice's theorem, but basically it says you can't say anything for sure about any non-trivial behavior of any program through static analysis. So with such harsh limitations, why would we care about this at all? Well, useful approximations are still possible, even if we can't be provably certain about a behavior of a program. And I could attempt to go into a more mathy explanation of what degree of certainty is possible with static analysis, but for me, the proof is in the pudding. And the proof is that static analysis has been used as a useful tool by programmers for decades. Maybe not as much in the ICS world, but it has been used generally in software development for a long time and fruitfully. And another reason I think static analysis is great is that it's kind of a relatively low effort intervention. It's automated, so it removes effort in that way, but also it doesn't introduce new attack surfaces as much as other interventions usually would. So we don't need access to the network. We don't need to install new hardware. We just need to run our code through static analysis program, and it can give us some feedback on that. We know this firsthand at the company I work for, that for good reason, a lot of companies are quite reticent to let you touch the PLC in any way. So some background about PLC programming. A lot of you probably already know this, but most PLCs are programmed in one of 5 languages. So they're defined in the IEC standards. Those are function block diagram, instruction list, sequential function chart, ladder diagram, and structured text. I couldn't find any hard data on this, but I feel pretty confident in saying that ladder logic or ladder diagrams and structured text are the most popular 2 programming languages for PLCs. And for this talk, I'm mostly going to focus on structured text because, as I said, it's one of the more commonly used languages, and also because it's most similar to programming languages we might be used to from other forms of software development. That was like an imperative programming language. It's most similar to Pascal syntactically. So tools already exist for other programming languages that are similar to it, so we can look at those tools for inspiration, making tools for structured text. And also, there's already an open source parser for structured text, and I'll talk about that later. So why do we care about programming our PLCs securely? Is that really worthwhile to try and do? Well, one of the core advantages we have as defenders over attackers in ICS is that we hopefully know more about our process than the attackers do. And so we can leverage that best at the PLC level by checking for plausibility of the program at various states. Also, if you're an acolyte of zero trust architecture, secure PLC programming is kind of like the embodiment of limiting the blast radius. For example, if your sensor gets compromised or an HMI gets compromised, you can limit the blast radius by programming your PLC securely so that if the PLC is sent bad values from somewhere over the network, it reacts in a way that doesn't just crash the entire control system immediately with any trivial value sent by an attacker. And also, as I discussed in the very first slide, we want to try and shift security left as much as possible in the development cycle. So if PLC programming is important, what constitutes secure PLC programming? There's various guidelines out there about how you should program PLCs. One of them is the PLC Open Guidelines. And they're great and they're extensive, but they're not really security focused. Some of the guidelines do have security implications indirectly, but it's not meant mainly for security. So what I like is the top 20 secure PLC coding practices list. I like it because it's specific to security, and I also like it because it was developed by a lot of people who are active in this community. In fact, I believe at least one person who was a contributor to it is speaking at S4 this year, and several people who were main contributors are here at S4 this year. So how can we apply static analysis to these practices? Well, I went through and I picked out some from the list of the top 20 that I thought would be most amenable to static analysis to go through and try and see what I could do with them. So those are modularizing PLC code, leaving operational logic in the PLC where possible, validating HMI inputs, validating inputs based on plausibility, and monitoring cycle time and memory usage. There are some existing tools already for static analysis. There are vendor solutions, Beckhoff, Siemens, Schneider Electric. They all have solutions of static analysis tools. It's not a comprehensive list. I'm sure there are others. Also, CodeSys has static analysis tools. CodeSys is a hardware agnostic PLC software development platform. The free version has some basic tools, and the professional edition has more. And also at this point, I'll mention model checking, which is a branch of static analysis that is very promising, but very difficult to implement well. And so I'm kind of considering that beyond the scope of this talk. But if you have a big cybersecurity budget, it's something to look into. I know people at Nozomi have worked on that. And lastly, there is the only open source tool I could find related to this is a tool called IEC Checker. So IEC Checker I referenced earlier in the talk as the thing that can build an abstract syntax tree out of structured text. It's open source, like I said, and it unfortunately is not necessarily meant for security. It tries to check for some of the PLC open guidelines, and also it's not currently in development, and it only really ever had one contributor to begin with. So you may be asking, if static analysis is so useful, why aren't there more tools? You know, the vendor solutions don't seem to be all that heavily advertised. The open source tool that is available isn't currently being developed. And I don't know for sure, but I think that a lot of it boils down to this misconception that PLC programs are just too simple to benefit from static analysis. And the argument often goes something like, well, so much of static analysis, usually in the software development world, is aimed at memory safety, and PLCs don't have memory safety issues because the IEC standards don't allow for dynamic memory. So I disagree with this for two reasons. One, even though the IEC standards only use static memory, many vendors extend the IEC standards to allow usage for dynamic memory, which allows for memory safety problems. And secondly, I don't believe that memory safety is the only thing that we can check for with static analysis. So an example of a static analysis concept that does not involve memory checking that is used a lot in the web development world is called taint analysis or taint checking. So given a tainted variable from an untrusted source, you determine what other variables derive their value from that variable. And as a paired concept to tainted variables, you have this concept of sinks, which are sections of the code that you do not want to be touched by the tainted variables. So this has been used for decades in a security context in web development. And it's used enough that it actually is built into some web development focused languages. So Perl comes with taint checking tools at the command line built in. So even with the limitations that I went over of static analysis, it does have a track record of success, at least outside of ICS. So an example of taint checking more concretely, in the IT world, normally the classic example of a tainted variable would be you have like an HTML input form and you're expecting a name, but you get a malicious person come in, and instead of just giving you a name, they use some SQL escape character, and then they have some malicious SQL code after that. This input gets stored into a variable. That variable flows through the program, and eventually it reaches a sink, which is a statement where you insert that string without sanitizing it into a database, and that ends up in the malicious SQL code being executed. To analogize that to OT, I'm going to use the Oldsmar water attack incident, which we now think was not a cybersecurity attack. It's just user error, but I believe it's still relevant. So in this example, the tainted variable is the sodium hydroxide set point on an HMI, changed either by a user or an attacker maliciously. And so that variable, that value gets stored to a variable somewhere in the PLC. We track where that variable goes through the PLC, and we find that it eventually reaches a sink, which is something that sets the valve position value for the sodium hydroxide in the system. So I tried to do taint checking in structured text, and the first step is to determine the tainted or the dirty variables. For the purposes of this, I just assumed that all direct variables were tainted. In the real world, you'd probably want to do some vendor-specific parsing to determine what variables are actually like input variables. And then using IEC Checker, I already have the abstract syntax tree, so you can just go through and recursively check the assignment expressions and find out what variables derive their value from the dirty input variable. And then you can check to see whether those tainted variables are ever used in like comparison and assignment operators, and if they are, you can say, well, this variable is probably checked for plausibility, So that's an analogy to sanitizing in the IT world. And if not, then you can warn the programmer that we think you have this tainted variable that reaches a sink, it reaches a point where it determines output values from the PLC, but you never checked it for plausibility. There's some other checks that are more general static analysis, not necessarily security focused, that we can implement that have security implications. So one of them is code duplication. If you properly modularize your code, it makes it easier to see security issues and to fix them once, and that's it, not have to track them down multiple places in your code. And so for this, I found a research paper that pretty clearly laid out an algorithm for checking for code duplication in C++, given the abstract syntax tree, and I just adapted that to structured text. And I should mention here, code duplication, and also what I'm going to talk about next, cyclomatic complexity. Those are often included in vendor tools and also the CodeSys static analysis tools. So cyclomatic complexity, in a security context, we can use this to check the PLC secure coding practice that says you should leave PLC logic in the PLC as much as possible and not in the HMI. So in a lot of programming platforms, you can write structured text for both the PLC and the HMI. Usually in the HMI, what you want to be doing is just like simple conversions to make things a little more human readable. You don't want to have actual like control system logic in the HMI. But sometimes there's some creep and you end up getting some control system logic in the HMI, and that's not secure. So we can just run a simple algorithm that's been used in static analysis a lot called cyclomatic complexity. That's a pretty good proxy for computational complexity and determine and warn the programmer that they've probably added too much logic to the HMI. You can also check for whether the PLC code monitors or logs certain values that are important for security. So scan cycle time and memory usage, they're usually only trackable by vendor-specific functions. And you can check for this by just doing a simple regular expression to determine whether the program ever uses a function call to check the scan cycle or the memory usage. And if they don't, you can warn the developer, hey, you should probably check for these values at some point in your program, or else you're not maximizing security. Another secure PLC coding practice is checking for unused ports and protocols and not using them. So there are vendor-specific libraries and configuration settings that are often stored in an XML file. And so for this, you could simply just go through the XML file, look at the libraries that have been imported, and then check for all of the functions that that library contains. And if none of the functions are ever used, you can warn the developer they've imported a library that they don't need, and possibly they've added another unnecessary attack surface to the PLC. So there's lots of potential future work in this area. You could extend this to other languages, so not just structured text, but ladder diagrams would probably be the next one to tackle because it's, as I said, the other most popular language. And also instruction lists would be interesting because theoretically, at least, all of the other IEC standard languages are supposed to compile to instruction list, so you can look at that intermediate language and statically analyze that and potentially be able to apply that to all of the other standard languages. Also extending this to other security practices, I kind of went through the low-hanging fruit and tried to implement testing tools for those, but there's lots of other ones that also are possibly amenable to static analysis that we can look at. Vendor-specific parsing is pretty big. There's lots of extensions that vendors do to the IEC standards that would require custom parsers. So in the real world, I imagine that's going to be an area of lots of potential work in the future for static analysis. And then lastly, of course, like tracking outcomes and tracking developer experience using static analysis tools. So in conclusion, I think I have a pretty modest conclusion here. I just want to convince you that static analysis is a useful tool to consider putting in your cybersecurity toolbox. If you're an IECS professional that touches PLC programming in some way or has some control over the development policies of PLC programming, I would encourage you to look at what options your vendor has available for static analysis and consider adding those tools to your development policy. And also, nowadays, a lot of organizations outsource their PLC programming to other organizations, so I would encourage you to see if it's possible to write into a contract that static analysis tools must be used in a certain way before you accept their PLCs programs. And then if you're a vendor, I would really encourage you to keep developing static analysis tools for your product if you already have them, and if you don't have them, to create some, and to not just develop static analysis tools that are the same as every other good practices software development guidelines, but to develop static analysis tools that are specific to PLC security. Because I think there's a lot of area for us to improve on PLC security with static analysis. And with that, I finished a little bit early, so I have time for questions. There's microphones to the left and right. If you have any questions, please go to the microphones.
Hi, Sam. Yeah, my name is David Ong. So my background is PLC programmer, and also a system integrator, and now a OT cybersecurity guy. So there are languages in the IEC, the 61131, right? There's 3, as you mentioned. And actually, in safety systems such as SIS, safety instrumented systems, safety PLCs, we don't use structured text, right? Typically, it's either a ladder logic, or in fact, more commonly, it's function blocks, and they are called limited variable language. Hence, it's not so kind of open form, high level, like a Pascal type of language or script, and less things can go wrong. Do you see that this is the way to go, so that you leave it in the hands of the OEM manufacturers versus the user or the programmer or the integrator having to do all the heavy lifting in terms of security and things that can go wrong, because there are many moving parts as opposed to lesser? You know what I mean? Mm-hmm. Thanks.
Yeah, so I take your point that ladder logic could be a more intrinsically secure language than structured text. I still believe that there's room to use static analysis tools to improve security for ladder logic as well. There's still the plausibility checking issue. You're going to have input variables and you're going to have output variables regardless of the language you're using. And at some point, you should be checking to make sure that the input variables are plausible, to make sure that attackers can't just crash your system through arbitrary fuzzing really easily. So hope that answers your question.
Yeah, thanks. And don't get me wrong, the tools that you mentioned, they're very useful and they're good. I'm just saying that for the extreme, safety PLCs, you don't want to use the structured text and scripts and so on. Yeah. So thanks for sharing. Thank you.
Yeah, that's a great point. If you're doing programming on safety instrumented systems, like you're saying, you definitely want to be using all the tools that you have, and possibly even a different language if it's more secure.
Hey,
all right.
I guess.
Yeah.
Next. Yes. So could you elaborate on the false positive issues of SAST?
Yeah. So as I mentioned, with how severe the limitations of SAST are, you are going to get false positives or false negatives pretty much whatever you do. And I would actually say that you should err more towards wanting to get more false negatives. That's not normally what we would say in cybersecurity, but static analysis is not a panacea. It's not the only tool you're going to be using. It's just kind of like a meta check on your PLC code. So I think it's okay to have false negatives. And if you have too many false positives, you're going to end up not using the tools. And so you're not going to get any benefit at all. So I would err towards, and you can pretty easily adjust how deep you check in your static analysis and stuff to get the right mix of false negatives and false positives. And at first, I would err towards trying to get more false negatives and less false positives, and making sure that you are able to use that in the development cycle with your developers. And then you can maybe move on to having more strict checks that possibly end up in more false positives.
Thank you.
Thanks. All right. Looks like no more questions. Thank you.